So what we are doing here is we are talking about chirality. And uh, to give a little primer into what we're talking about is we're talking about the 3D nature of molecules. All right, so that's really all that we're going to be talking about. This is the crux of everything that we want to say. And basically, the big point that I want to impress upon you at this stage in the game, let me situate my monitor a little bit better, need a bigger desk, is that molecules are not flat, right? They exist in a 3D world and they exist in a way where the 3D nature of the molecule has to be taken into consideration. So, with that in mind, we have to come up with a way of describing 3D molecules. And so, one of the ways that you might have seen in class so far, or if you watched the video previously, is we come up with the wedge and dash system, in which we say that when something's on a wedge, it is closer to us, and when something is on a dash, it is further from us. Has he started to go, or has she started to go over this in class? Yeah, okay. And the representation that I always like to give is, say you have a piece of paper or a table or something like that, and we have our molecule on the table. Then a wedge would be like it coming up and out of the table, like directly sticking straight up out right towards us. Boop, just like that, coming out of the page. Versus what a wedge bond would be is like it's coming down and through the table. So here's some nice legs to our table. Stuff like that. Good old legs. And so our wedge bond is below the table, kicking you in the feet. Okay. And with that in mind, we can start to talk about uh, how to classify these drugs and how to talk about them, and more importantly, how to name them. Because we can't just call something, oh, that's a wedge molecule, because it's not entirely accurate. Because just because something's a wedge doesn't mean the wedge is the same over every single kind of molecule. All right. So what was developed was this con-angled Prelog system of describing 3D molecules. Con-angled Prelog. And a lot of times you'll just see this kind of called the CIP system. A lot of times you'll just hear it referred to as the R and S nomenclature, but they all mean the same thing. They're all describing the same thing, which is a way of describing molecules uh, universally. And so the Con-angled Prelog system relies on chirality. And chirality, if we remember, is when you need a couple of things to have chirality. First of all, you need a sp3 hybridized carbon. That carbon needs 4 different groups and uh, and there should be no symmetry within the molecule. Within molecule. WN is within. All right. So the fact that if we have these 3 pieces of information that all kind of inscribe, this last piece of information has more to do with isomers. So when we get to the end of this, we'll talk more specifically about this, versus these 2 pieces of information are more for chirality. But all 3, it's good to be able to determine all 3 pieces of these uh, on a molecule, because It's what's going to really drive what's going on. All right, so before we even jump into RNS, we have to be able to describe where chiral centers are, okay? And so let's say that we just take a molecule like this. And the question that I'm going to be asking is circle the chiral carbons. And so we go through our criteria. We look for sp3 hybridized carbons, which we know sp3 hybridized carbons are ones that have 4 bonds, right? Because we know from back last test, we learned about the steric number. And to be sp3, you need to have a steric number of 4, which, so sp3 needs a steric number of 4. And we learned that the steric number could be, it could be made up of lone pairs and bonds. But if we're talking about carbon, carbon should not have lone pairs. It should have really bonds going on. And so when we have sp3 hybridized carbon, we're talking about a carbon with 4 bonds. Okay, so we want 4 bonds. And according to our rule, again, what kind of bonds do we want? We want 4 different bonds, okay? So we want it bonded to 4 completely different separate things. So easy ways of determining non-chiral or achiral carbons. Is it going to be these ones here that I'm highlighting in pink? Well, these are sp3 hybridized carbons, but this is an CH3 group, right? This is a carbon that's bonded to H, H, and H. So are these 3 different groups? No, these are 3 of the same group. So this is not a chiral carbon. Same thing with these 2 inner circles right here. These are CH2 groups. So we have it bonded into the rest of the chain, but then we have H and H, right? So those are the 2 same groups. So these are not chiral either. So don't confuse yourself and start checking every carbon, because honestly, we're only looking for carbons that have things bonded to them, whether it's another carbon or if it's, an oxygen or a chlorine or a nitrogen or something like that. So you can almost entirely just look for where the obvious chiral carbons can exist. We're not going to trick you and be like, oh yeah, this thing is chiral. It's never going to be chiral, all right? As 3 of the same bonds or just 2 of the same bonds, all right? So chiral carbons can be, I don't want to say that they're rare in a molecule, but there's generally less chiral than there are achiral. It's the way that I want to say it. All right, so, well, that leaves that we have these two carbons, right? And so let's make a shopping list. So let me actually do some labeling for us. So we'll say that's 1, 2, 3, 4, 5, and 6. And so for C2, for carbon 2, what are the 4 groups we have? 1, 2, 3, 4. Let's make our shopping list. Well, obviously, one of the first groups that we can identify easily is that oxygen, right? That OH group. Another group that we can easily identify is that hidden hydrogen, right? So I'm going to put him at the bottom just because I'm in charge, so I get to do what I want. And then what do we have left over? Well, we have C1. Oops, wait, do this in the magenta. We have C1 and we have C3. And we have to make sure that C1 and C3 are different from each other, right? Well, C1 is a methyl group, and C3 is that, CH2 group. So, we could write in CH2, but obviously we can see just from visual examination of this molecule that to the left, that C1 carbon is much different than that C3, right? Because this C3 leads on to the rest of the molecule and it's, nice and complicated over here, whereas C1 is nice and simple. So obviously C1 is different than C3, okay? If this is true, if we have 4 different groups, then this molecule is chiral. Or sorry, this carbon is chiral. So we have a chiral carbon. Very nice. All right, let's do the same thing for that C5 carbon, the one with the chlorine on it. 1, 2, 3, 4. And obviously we have that chlorine, right? Because that's an easy one to find. We have C6, which is a methyl group. We have C4, which, goes on to the rest of the chain and is obviously different than C6. And then our last group is, don't forget, that little hidden hydrogen, right? And so once again, do we have four groups? Yes, we do. So C6 is, or C5, I should say, is also chiral. All right. And so just because you have a chiral center does not mean that your molecule overall is chiral. And if you go back to the other session that we talked about, is that if you have any kind of symmetry going on in your molecule, then that will get rid of, that means that you don't have a chiral molecule. You may have chiral carbons, but the molecule as a whole is achiral. Okay, so it's an important distinction that we're talking about. All right. Uh, and what that means is, the reason why I labeled it like this is that remember that sp3 in four different groups is what defines chirality. We could fill it and we could say it more accurately, chirality of carbons, versus the no symmetry is really talking about things like isomers. So when we talk about enantiomers or diastereomers, or later we're going to talk about meso, because that's the thing people always get confused about. All right, let's do another practice problem. Um, I don't know. Maybe we are. Um, I'm gonna give you guys a nice, big, complicated one. So this is glutathione, which I believe is what I believe it contributes to, like, the umami flavor of a lot of different foods. Uh, I believe, or might that just might be glutamate on its own. I can't remember. I'm sure this does it as well. I think this is what gives the kind of really pack a punch flavor to onions and garlic and stuff like that. That might be something else, something with sulfur in it. Anyways, so we're talking about glutathione, and the question is, circle all of the chirality centers within the molecule. So I'm just going to label kind of randomly. Obviously, I'm not labeling for naming. I am just labeling so that way everything is labeled so we can talk about it. And so what we can go through is, first things to know is that we should cross off places where we definitely know chirality should not show up, right? So we know it's not going to be on carbon 6 because carbon 6 is not sp3 hybridized, nor on carbon 11 because carbon 11 is sp2 hybridized. Carbon 14 is sp2 hybridized. Same with carbon 3. All right. So those are the kind of sp3 or the ones that are not following the first rule. And then finally we can cross off, position 4 because that is not doesn't have 4 unique groups. Same with 5, 13 as well. And then people ask me all the time, well, can nitrogens and sulfurs and can all these other things be can they be chirality centers? Of course they are. Or of course they can be, I guess I should say. So is this nitrogen here sp3 hybridized? It is. This is sp3 hybridized. But it needs to contain 4 different groups, and I don't believe that lone pairs count as groups. So this nitrogen does not count, and neither would this nitrogen at position 7. All right. Likewise, this nitrogen over here is sp3 hybridized, and it has 4 groups, but it is not 4 different groups, so it does not count. So what does that leave us? It leaves us position 2, position 8. Oop, I forgot to cross off. 9 is not sp. It doesn't have 4 different groups either. So we have 2 chirality centers. We have it at position 2 and position 8. All right. And the same thing could be said about the sulfur. The sulfur does not have 4 unique groups bonded to it, so it doesn't count either. All right, so what I'm going to do is I'm just going to redraw the portions that we're going to talk about. So we're going to redraw position 2. And we're going to redraw position 8. Cool. So now that we have these drawn out, now we can talk about them specifically and we can make a shopping list. So for carbon 2, what are the 4 groups that we have bonded? Well, we have off to the left, we have that NH3 plus group so that's definitely unique. We have this carboxylate group up to the top, so that's totally unique. And then we have C4, which is unique to the other 2 groups. And then what's our last group bonded in? Don't forget about the hidden hydrogen. And so we can say that these are all 4 unique groups and an sp3 hybridized carbon. So this is a chirality center or a chiral carbon. Interchangeable words. Chirality center, chiral carbon. And then same thing here. We can make a shopping list for position 8, carbon 8. And we can say that carbon 8 has, for its 4 groups, it has this nitrogen over there. So this nitrogen that's part of the amide. It has that carbonyl group on position 11. It has this carbon 9 that eventually bonds into that thiol group. And then finally, what's the last group? Don't forget about the hidden hydrogen. All right. And so are these 4 unique groups? Yes, they are. So is position 8 chiral? Yes, it is. All right. The best way of getting good at these things is through practice. Okay. There's no trick to identifying chirality centers. There's no tips I can give you other than you just got to practice. There's tons of practice out there. Go look at the steroids. Steroids have tons of chirality centers in there. Or go look at drug molecules. Drug molecules have tons of chirality centers, and I'm sure you can find tons of practice. All right. How do we feel about this? Good so far? Is this making sense? Cool. Now that we've kind of gone over how to find chirality again, now we need to be able to describe what's going on, which is where we get into the conangled Prelog system. Okay? CIP. So what The Coningo-Prelog system does is it allows us to describe the 3D nature of drugs, or molecules, I should say. Okay. And what we're going to be using is we're going to be using R to represent a clockwise rotation. And we're going to be using S to describe a a counterclockwise rotation. And I know that S stands for sinister. I can't remember what R stands for. I think it's reticulum. I can't remember. Go look it up. But basically, what we're going to be saying is that S is a left-handed rotation, whereas R is a right-handed rotation. And so what you're always going to see me say is that clockwise, I'm going to abbreviate to CW, and then for counterclockwise will be CCW. Okay, so this is the kind of notation that we're going to say. And just because I get asked this all the time, and people always assume this is true, okay? Wedge does not mean R, and dash does not mean S, okay? So people ask me this all the time. This is the assumption that people come into all the time whenever they are studying RNS is they think this is the relationship. It is not true, okay? You can be S and have a wedge bond. You can be R and have a dash bond. They have no bearing on each other. Okay? So this relationship of wedge equals R is not true. So if you have to repeat that to yourself however many times it takes, just like acids donate, get it in your head. All right? Because I don't want to see this written in your notes anywhere because I will kick you in the shin. So now that we've done that, let's take a look at our original chiral molecule that we worked on. And what I'm going to tell you is that we cannot determine R or S of a molecule unless if we're given what the 3D nature of the molecule is. I don't know why I keep saying drug. All right. We cannot determine the 3D nature of the molecule unless if we are told about what the 3D nature is. Now, they could tell us the RNS, and then we'd have to determine the wedging or dashing, or they could give us the wedging and dashing, and we have to determine the RNS. All right. So as of right now, I have nothing in this molecule that tells me what I need to know. So what I'm going to do is I'm going to put both of these groups on the wedge. Oh, now I have some 3D information that will help me. And now I can use the conangled Prelog system to determine RNS. All right. Step one, locate the chirality. Oh, we've already done that. We already determined that this is just a matter of practice, right? So we've already determined that these are where our chirality centers are. Let me put in the labeling again. All right. And what part of that is making sure that we know what our four groups are. So let's just copy our shopping list from the other problem that we did. So we've already done this, right? Step two, didn't really leave myself room to write this. So if you did, you can write it over there. But step two is now we're going to rank the four groups. And we're going to take each carbon at a time. Like we're going to do all of C2 and that's for C2. And we're going to do all of C5 and that's for C5, right? So we're not going to be comparing C2 with C5. Everything is intrinsic to the one. And then what I'm going to tell you is that once we do that, we're going to determine the sweep. Or the better word that we've already used before is determine the rotation. So clockwise or counterclockwise. And then we're going to make we're going to do our check. Or yeah, our check. We'll call it that. Cool. All right. How do we rank our four groups? Well, ranking is done based on the atomic number of the group. Okay. Ranking is based on atomic number. All right. And what I'm going to tell you is that it's first point of difference. And we're going to do a problem in a second where this is going to be a little bit more evident, but I just wanted to make sure that it was going to be put in the right place. All right. So let's do some ranking, shall we? So look at the atoms that are directly bonded to carbon 2. And you know what? I'm going to need more room. So I'm just going to copy this. And put it right there. So let's look at C2. What are the atoms bonded to C2? Well, we have that oxygen, right? We have C3, we have C1, and we have a hydrogen, right? Now, notice that I just said it was the oxygen, right? Because it's the oxygen that is bonded into the carbon. Same thing with C1 and C3. It is the carbons that are bonded into carbon, not whatever comes next to it. So it's where we're seeing the first point that goes. And then if we need to, we're going to keep going along and along and along till we find a point of difference, all right? So out of the four initial bonds, who has the highest atomic number, all right? Well, the highest atomic number, you know, hydrogen is atomic number 1. These are atomic number 6. And oxygen's atomic number 8, I believe. I need the periodic table in front of me. Periodic table. I feel like I should know this off the top of my head. Yeah, so periodic, so carbon is element number 6, oxygen is element number 8. So it has the highest atomic number for our 4 initial bonds. So it is going to get the highest priority. So 1. Now, who's better, carbon or carbon? Who has the higher atomic number? Neither one, right? Because they're both element number 6, so they're equal to each other. So we'll come back to them in a second. But who do we know definitely loses, right? It's going to be hydrogen, because hydrogen has atomic number 1, so it's going to be the last of our 4 groups. Now, I just want to let you know that some teachers, they do the same ranking, but they use letters. And you'll hear the mantra later on, D is down. This is what they're referring to, okay? I just default to the numbers. I don't know why, but it gives you the same product, all right? So whether we're using letters or we're using numbers to kind of describe the ranking. So now we are at a pickle here, right? Because carbon 1 equals carbon 3 in terms of atomic numbers. So we have to look at what each one of those is bonded to. And what we can say is that carbon 1 is bonded to 3 hydrogens versus carbon 3 is bonded to 2 hydrogens and carbon 4, right? It has 2 hydrogens and carbon 4. So hydrogen is the same as hydrogen. Hydrogen is the same as hydrogen, but who wins, hydrogen or carbon? Oh, carbon wins. So now C3 is going to be given priority number 2, or we could say it's priority B. And carbon 1 will be given priority number 3, or priority C. Okay, so just to fill in what we're going over here, we have 2, 3. 1, 2, 3, 4. Perfect. So we've done the second part of the Cone-Angle Prelog system where we determined the ranking. Now we have to, what did I say came next? Now we have to determine the rotation, okay? So what I want you to kind of fill in underneath that, I'm going to rewrite it. Step 3, determine the rotation. Hopefully you have a little bit of room. Is we have to look and make sure group 4 is down. Or a lot of times you'll hear D is down. All right. And let's talk about why. All right. So what I'm going to tell you is if the sweep, which can also just be said the rotation, of groups 1, 2, and 3 is clockwise, then the rotation is R. However, if the sweep or rotation of 1, 2, and 3 is counterclockwise, the rotation is S. If, big if, that's on the dash line, that's, you know, underline this, put it in bold. If 4 is down. And what do I mean by that? I mean that group 4 is on the dash. And so what I like to say for this is that I like to simplify this down and say the rotation is true if 4 is down. Okay, so the rotation that we're guessing, you know, clockwise is R, counterclockwise is S, is true if group 4 is on the dash. Otherwise, we're going to take the opposite of what we think the rotation is. And so what this is it's doing our check, okay? So this is where we are doing step 4, the check. Step 4, the check. So let's take a look. Let's see what we're trying to talk about. So the best thing to do is to take our rankings and to put them directly onto the molecule the way that the molecule looks right now. And we're just going to look at groups 1, 2, and 3 for now. And we're going to say that to get from 1 to 2, I have to rotate to the right? I have to go clockwise. And then to get from 2 to 3, I have to go clockwise. And to get from 1 to 3, I have to go clockwise. So what's the rotation? Clockwise. And what did I tell you? Whoops, wrong layer. I said that R is a clockwise rotation, right? And so what we're going to see is that this rotation is R. But wait, didn't you tell me that wedge doesn't mean, didn't you say this? Didn't we say that earlier? Yeah, I said that earlier, but that means that it's not always true. Sometimes it's true, but sometimes it's not. So this is why I'm saying that, because a lot of times people just see wedge and they go, oh, it's R. That's not true. It happens to be true this time, but it is not true all the time. Okay? So now we determine the rotation. We said if it's R or S, and now we have to look at the check. Okay. And what is the check? Well, we look at group four. Group four is that hydrogen. And if what we determine is that, oh yeah, group four is on the dash. So the rotation is true. And I like to put a big check mark right there. Or sometimes what I do is I do R becomes R. And I put a big check mark right over that. Let's go through this and let's go through it and talk about it one more time. We found the chirality. We checked to make sure that it was chiral by checking all the groups. Then we determined the ranking of the four groups. We determined the rotation. We said that it clockwise, and clockwise means R. And what we checked is we made sure that group four was on the dash. And since it was, it meant that R is R. The rotation that we guessed is true. And so we can say that the rotation of C2 is R. So carbon 2 is a right-handed rotation. Very nice. All right, let's do carbon 5. Here we have carbon 5. We said that we have four groups. We have chlorine, hydrogen, C6, and C4. And while it's all well and good to draw out what's going on, we really can't be doing that when we're doing an exam, right? It's way too much work. That's way too much space that we don't have in order to be writing things out. So what we have to get good at is doing the shopping list, okay? And what I mean by that is right off the bat, just by looking at their shopping list here, who can we say is number one? Or who can we say is last, right? We know that hydrogen is definitely last, right? Because it is the smallest atomic number. Boom, easy. And who can we say is first is chlorine, right? Because chlorine has it has an atomic number of 17. And so it's definitely bigger than carbon, so boom. But now we're at an impasse, right? Because we have a difference between carbon and carbon, and they're equal to each other, right? So what I want you to do is write a shopping list for them. And what we're going to do is we're essentially going to write what are the three other bonds that are on carbon 6 and carbon 4, so we can just compare those directly. And we're going to write them in descending atomic order. So what do I mean by that? Well, carbon 6 is bonded to all hydrogens, right? So he's just going to be hydrogen, hydrogen, hydrogen. HHH, right? Carbon 6 is only bonded to other hydrogens. Versus carbon 4 is bonded to C3, hydrogen, hydrogen. And so what I can see right here is that, oh, here's my first point of difference. Carbon is bigger than hydrogen, and so what I can say is that C4 wins and C6 loses. Let's say, for instance, that carbon 6 was bonded to another carbon. Well, then we'd have that written there, and we could say, oh, that doesn't count, and we could cross them off. So that's why writing a shopping list like this is really important, because it's a very condensed way of making sure that we're doing it right. All right. So I really, really recommend getting into the habit of writing your shopping lists so that way we can save space and time as we're doing it. Also get into the habit of numbering your everything. All right. You saw me on when we were doing glutathione that, I was labeling every single atom I could because I want to be able to give things labels for when I talk about them. And so it helps cut down on what we're doing, right? So what we can go from here is we can relabel where our priorities are. So chlorine gets 1. Towards C4 gets second priority. Towards C6 gets the third priority. And then, of course, we know that there is a nice little hidden hydrogen right there on C5. And so what I can see going on is that I have a clockwise rotation between all of my molecules. And so what does clockwise mean? Clockwise means R. And so now I have to check. I'm guessing that it's R. Is 4 down? Is the fourth group on the dash? Yes, it is. So the rotation is true. So carbon 5 is a R rotation as well. All right, this is all well and good, I hear you say, but what happens if we had the opposite? So let's copy, the molecule itself. So let me actually, whoops, come on, come on, I believe in you. All right, let me just erase this and put it up above so that way I have some room. What you could do is redraw this molecule while we're waiting. So we have our good molecule here. But what I want to do now is I want to put the chlorine on a dash. Do I want to put the chlorine on the dash? You know what? Never mind. Let's just do a new molecule, shall we? My bad. Ha ha ha. Sorry. I want to do a new molecule. All right. New molecule time. Um, let's put another chlorine over here. All right. Let's do some labeling. So I'm going to put carbon 1 right there. And first steps first is to find all of the chiral carbons, right? So quite obviously we can see that it's, carbon 1, carbon 2, carbon 4, right? It's not going to be 5, 6, and 3 because those both have hydrogen, 2 hydrogens on it. So those aren't going to be chiral carbons. And then from here, what we can do is we can start to do our shopping list, right? So let's start with carbon 1. Carbon 1. And we know that there should be 4 groups on carbon 1. And what do we have going on? Well, one of the bonds that we have is to that oxygen. One of the bonds that we have is towards C2. Another bond that we have is towards C6. And what's the last bond we have? Well, it is that nice hidden bond of that hydrogen. And don't forget, if we see a dash bond, then that means that there must be a wedge bond, right? So if the oxygen's on the dash, then it means the hydrogen must be on the wedge. If you have one, you have to have the other. And why don't we we'll go through everything at once. So let's determine which one of these is highest in priority. So out of the four initial bonds, who's definitely going to be lowest? Oh yeah, that's hydrogen. Hydrogen always loses. Who's definitely going to win? Well, that would be oxygen, right? And now who wins carbon to carbon? Exactly the same. So now we have to see what each one is bonded to. So C2, and well, we'll do C6 first because that's a little bit simpler. C6 has is bonded to C5 and two hydrogens, right? C5 and two hydrogens. C2 is bonded to a sulfur, C3, and it has that nice hidden hydrogen for us. How did I get these? Well, I'm looking directly at C2 and I say C2 is bonded to that sulfur right there. It's also bonded to the carbon and it has that hidden hydrogen. Well, isn't it bonded to C1? Well, yeah, it is, but we've already counted that, right? So we don't need to double count C1 because they both have C1, right? Because we're trying to branch out and away. So from here we can say, oh yeah, sulfur has a greater atomic number than carbon, so we can say this is where our first point of difference is. So C2 is going to win. Boom. Now, uh, now we're good. We can keep going. Cool. So now what we should do is we should place our numbering, our ranking onto our molecule. And notice what I'm doing here is I'm labeling where the numbers go in between the bonds between carbon 1 and carbon 2, or in between carbon 1 and carbon 6, all right? And what that does is it helps me notice where the ranking is going, okay? It also keeps things nice and tight around what's going on. The other thing that you could do is if your molecule is just getting a little bit too messy, is just kind of push it off to the side, right? Because this is the same shape as that, except, I'm not talking about any of the molecules. We only care about where they are relative to each other. And what we can see is that one is uh, going clockwise to two is going clockwise to three is going clockwise. So this is a clockwise rotation. And what does clockwise mean? Clockwise means R. Okay? Clockwise means R. And now we're going to check, is D down? Is D on the dash? No, D is on the wedge. So it's the reverse. So we have to take the reverse of what our guess is. So what is the true rotation of carbon 1? It is an S rotation. S rotation. All right. Notice what I did once again. I guessed that the rotation was R because it is a clockwise bond. But because D is not down, because 4 is not on the dash, I have to take the reverse of my guess. So it is uh, my R guess becomes the S rotation, the reverse of my thinking. Cool. Let's go on to the next one. So we are talking about C2. C2 has 4 bonds. And what we can say is that C2 is bonded to sulfur. C2 is bonded to carbon 3. C2 is also bonded to carbon 1. And carbon 4, and the last bond here is a hydrogen, right? And so same thing that we can say is that hydrogen is of course going to lose, sulfur is of course going to win. And now we have to do our shopping list because carbon equals carbon. And just for practice, we can say that C3, this guy right here, is bonded to C4, a hydrogen and a hydrogen. And C1 is bonded to an oxygen, C6, and a hydrogen. And once again, we see that first pointed difference where we can say that C1 wins, right? Because oxygen is bigger than carbon. What happens if they were the same? What if, miraculously this thing had a hydrogen as well? Well, we go to the next point of difference and we say, okay, carbon's bigger than hydrogen, right? So we can always keep going down the list. What if they're all equal? Then we have to go another step, which I will show you in a second. Also, uh, my favorite uh, thing in chemistry. It has the dumbest name, but it's the best thing. All right. So what we can do is we can fill in our rotation. So we could say that, this is, I need a new color. To purple. This is 1 towards C, towards carbon 1 is 2, towards carbon 3 is 3. Gets confusing. But what we can say is this rotation looks like this. And so what kind of rotation is this? Well, we are going counterclockwise, right? This is a counterclockwise rotation. And what does counterclockwise mean? Counterclockwise means S. Is the fourth group on the dash? Well, yes, it is. So the rotation is S. So what is the rotation of C2? It is S as well. And this is why I had you know, I prefaced this with saying is that wedge doesn't always mean R. Here we have a wedge bond, but it's an S rotation. All right. Here we have a dash bond and it's an S rotation. So just because you have a wedge or dash does not automatically mean what the answer is. Just to erase this so I have some room for myself. Let's do this last carbon. C4. We're doing on time. Good enough. C4 has 4 bonds. We have a chlorine and a hydrogen, and we have C5 and C3. Ooh, I'm going to need more room. We have chlorine and a hydrogen. We have C5 and we have C3. And of course, once again, we can say that, I'll do it in pink, chlorine's going to win, the hydrogen will lose. Carbon is equal to carbon, so we have to check their shopping list. And what we can say is carbon 5 is bonded to carbon 6, a hydrogen and a hydrogen. Carbon 3 is bonded to carbon 2, a hydrogen and a hydrogen. Oh, but wait, these are the same, right? Who's better, carbon or carbon? They're exactly the same. Who's better, hydrogen and hydrogen? Exactly the same. Hydrogen and hydrogen, exactly the same. Shit. What do we do now? We have to go to the next layer. All right. So now we're going to go to carbon 6. So what we have going on for carbon 6 is bonded to carbon 1, a hydrogen and a hydrogen. And carbon 2 going along is bonded to a sulfur, a carbon 1, and carbon 1 and a hydrogen, right? And now, we can say, okay, now the sulfur wins. And so we can say that C3, this branch going towards C3 will win. And so now we've made our determination. We can put this on the molecule and we can say 1, 2, 3, which looks like this. And what kind of rotation is this? This is a counterclockwise rotation. What does counterclockwise mean? Counterclockwise means S. And is our fourth group, our hydrogen, on the dash? Yes, it is. So S is S. So as it turns out, all 4 of these carbons have the same rotation. They are all S carbons. Cool. What does this mean? Okay. What is important about this is that what we can do now is we can describe the naming of this molecule. So what I would tell you is, oh, my mouse died. I wonder why it's not working. What I will tell you is that if we were to go and name this I don't even have any room. If we were to go and name this compound, it would be at the name of this compound would be cyclohexanol 2-thio. It would be 4-chloro 2-thiohydroxy, maybe. Thiohydroxy. I think that's how you would say it. Cyclohexanol. And so basically what I want you to know is that at the beginning of your naming, this isn't important. If this didn't make sense to you, that's fine. We'll do a session on naming in a second. But what I want you to know is that at the beginning of your molecule, what you're going to do now is you're going to put stereochemical designators. And so what would it be? It would be 1S for carbon 1, 2S, 4S. So that's what the important thing is for Con-angled Prelog, all right? That we can now describe what the rotation is of this molecule. But, what does this matter? Well, what this matters is that if we gave this name in a paper or if we read it somewhere, we could, from the fact that it gave us 1S, 2S, 4S, we could then go and draw the molecule the way that it's given, okay? So we would be able to get the wedging and dashing correct now because of what's going on. All right, so let me maybe I can simulate this for us. So, whoop, there it is. If we what I did is I typed in the name into this generator called Opsin. It's a great, great thing. And what we notice is that if I left out the stereochemical designators, I'd only get this, right? And this does not have any 3D molecule, 3D nature of the molecule, right? It doesn't tell us anything. Versus when I put in the stereochemical designators, what do you notice? Oh, they're there now. So now I can tell what the 3D nature of the molecule is. So that's why we use the Conangled Prelog system, because it's a way of saying put a dash bond there, put a wedge bond here. And what we'll do in a second is we'll go from name to structure. All right. How are we doing so far? Is this kind of sort of making sense? Yeah. The big thing is with molecules, and this is it's just practice. You have to practice, practice, practice. Um, Often, why I find people do not do well on this exam is that they spend so much time worrying about how complicated RNS is instead of actually practicing it. Some notes about ranking. Ranking um, uh, continued. Okay. Let's say that we have this molecule. And all I want us to do right now is focus on this carbon right there, okay? All right, so I'm just labeling positions so that way we can talk about it. But I want to be able to talk about a couple of kind of important things, all right? So what I want to say is this. If we did the shopping list for carbon 3, what do we notice? Well, obviously, of our 4 bonds, we have hydrogen is on that, nice hidden bond right there. We have a chlorine, and then we have C4 and C2, right?
What
C4.
exactly are you looking at? Like, because,
Oh, can I not?
yeah, no.
Wow. Can you see it now?
Oh, yeah, yeah.
My bad. I'm glad you're here because I would have just kept going. All right. So to repeat what I was saying, we're going to be going over the kind of an expanded rule set for ranking. All right. So when we look at this molecule here, what do we notice? Well, we have a ketone functional group. We have a alcohol functional group. We have this methoxy functional group. It's an ether here, chlorine as well. And uh, what I've done is I've labeled them just for positioning, and I have drawn out what the shopping list is like. All right. So I'll give you a second to kind of copy things down. All right. So we have our shopping list. And so obviously we can say that, who's going to win? Chlorine's going to win. Hydrogen's going to lose, right? Boom, right off the bat. But now we have to figure out what's going on with carbon 4 and carbon 2. So what is carbon 4 bonded to? Well, carbon 4 is bonded to an oxygen. It's bonded to an oxygen. And it's bonded to a hydrogen, right? Don't forget that there's a little hidden hydrogen right there. What is carbon 2 bonded to? Well, it's bonded to carbon 1, which for a reason that I'm going to tell you in a second, I'm going to put last. But how do we describe a double bond? Well, this is what I'm going to tell you. The single bond is a real oxygen, just as real as oxygen 5 and oxygen 6. It's real, it exists, and everything like that. But we need a way of describing this pi bond, right? We need a way of saying what this pi bond is. So, just in time for Halloween, we're going to talk about oxygen, but we're going to give it this little symbol, this little zero up in the top right corner. And what it's called is a ghost a ghost oxygen, or a ghost atom. This is a ghost atom. Ooh, spooky, right? Ghost. So, what I want you to know is that who wins here? Real oxygen or real oxygen? They're exactly the same, right? Who wins here? Real oxygen or ghost oxygen? For all intents and purposes, they're exactly the same. So, what really determines the ranking here is the carbon, all right? So the reason why I tell you this is because it comes up way more common than you think. All right. So you can go through and you can determine the chirality of this and you can practice. What I'll tell you is that this molecule is, what would it be? It'd be one, two, three. So it'd be, this should be an R rotation if I've done it correctly, quickly in my head. One, two, three, clockwise. Yeah, should be R. So you can go through and you can practice that. But what I want to show you is, where does this sort of thing show up? Well, it's really common when you have things like benzene rings. By the way, in case people are wondering, carbon 4 is another chiral center, and you could practice and go through and figure out what the chirality of that one is as well. All right. So if we take a look at this, what we can say is, for the carbon that we care about, we have 4 groups. Uh, let me do some labeling here. So for carbon 1, we have 4 groups. Who are the 2 obvious ones to pick out is oxygen and hydrogen. And we have C2 and we have C5. And what we can do is we can create the shopping list. So we know that oxygen will win, hydrogen will lose, blah, 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 blah. But now we have to figure out what's going on between carbon 2 and carbon 5. Carbon 2 is bonded to carbon 3, bonded to carbon 4, and don't forget a little hydrogen right there. Carbon 5 is bonded, has a real definite bond to carbon 6. But it also has a ghost bond to carbon 6, because it's a pi bond, right? And it also has a real bond to carbon 10. So who wins here? It would be carbon 5, because we have that point of difference right there. And so we have this going on. And so I believe this is an S rotation. So if people want to do it out and double check that I've done it right in my head, it should be an S rotation if I've done this correctly. One, two. Yeah, it should be S. All right. So this is one of the big things that always ends up getting people confused, is that double bonds, triple bonds are the same thing. If you have a triple bond, it just means you have 2 ghost carbons, all right? It doesn't mean that we can't count them. It means that we just have to count them as ghost bonds. All right. So with that in mind, um, what we can do is we can go on to going from the name to the structure, which people tend to find is a little bit more complicated. But once again, I find it's mostly because that they just don't practice enough, or they often what happens is that people get really uh, frustrated with doing things like this, and then they feel like they can't do it, and then they just stop doing it, which is just no good. Can't be having that. So what I'm doing is I just want to make sure I'm getting the name correct. Um, all right. So we have going on. Let me do this even on a new page. The molecule I'm giving you is 2R, 4S, 7 amino, 4 chloro, heptan 2 ol. So I realize that you might not have gone through and done naming functional groups yet in class. That's totally fine. If this kind of drawing the molecule, like identifying doesn't make sense, we're going to do something about nomenclature later. Um, so just send me a text if it doesn't. But basically, we can identify different pieces of this molecule or this name, right? First thing I zoom in on is hept, right? Because what this does is it tells me the longest chain, right? So the number of carbons in the longest chain. So what I should do is I should draw 7 carbons, right? 1, 2, 3, 4, 5, 6, 7. And what do I notice as well is that I have AN afterwards. So this tells me the type of chain. So AN tells me it's an alkane. So I only have single bonds going on. So this is I don't see any double bonds anywhere. Likewise, I have this 2-ol, and this is the highest priority group. And what does OL stand for? Well, this is telling me that there is an alcohol group, which is where we get that OL from. And where is it? It's on carbon 2. So what I can do is I can label 1, 2, 3, 4, 5, 6, 7. And on carbon 2, I have a good old OH group. What else do I have? Well, I finished the end of my molecule, so now I can kind of go on to the middle of my molecule, and I see a 4-chloro. So obviously these are all substituents. And what do I have? I have on carbon 4 a chlorine, and on carbon 7 I have an amino group, which is just a nice old NH2. All right. So now, we've drawn the molecule, but now we need to do this last part, which is the stereochemical designators. The stereochemical designators. All right. And what I'm going to do is it tells me exactly where these stereochemical designators are. They're on carbon 2 and on carbon 4. So what I should do is for my functional groups that are on carbon 2 and carbon 4, I should erase the bond that's here because it's going to be replaced by a wedge or a dash bond. All right. And I don't want anything in the way that's going to disrupt what's going on. Okay. So what did we do? Step one, we drew the molecule. Step two, we erased the stereochemical bonds. And then step three, we're going to determine, basically take the reverse of what we've done in, for when we were drawing the molecule, or for when we were naming the molecule, or we were finding the rotation, what we did previously. So what do we have? We have 2R, right? So what does R mean? R means a clockwise rotation. And so what we can do is we can look at carbon 2, right? And we can do the same thing that we've done before. We know that carbon 2 should have 4 groups on it. We can say that the hydrogen that's on carbon 4 is going to lose. The oxygen on carbon, sorry, the hydrogen on carbon 2 will lose. The oxygen on carbon 2 will win. So, same thing that we've been doing all this time. And then what else do we have left over? We have C1 and we have C3, right? C1 and C3. Now, just by visual examination, I can see that C1 is a methyl group while C3 goes to the rest of the chain, right? So just by visual examination, I can say that C3 will win, right? Because I know that methyl group is only hydrogens, whereas this will lead on to at least another carbon, and at least another carbon will beat C1, okay? So this is another part that as you become more comfortable with doing conangled Prelog, with the RNS system, you're going to be able to just look at them and be able to say, okay, this one beats that one, okay? So once again, we're moving from drawing out the chains, like what we did here, moving from this to being able to just do our shopping list, to then eventually moving to just visual examination on its own. So that's the progression that we want to get through. If you're still on drawing it out, that's totally fine. Oh, I think I will be right back in 1 second. Okay, sorry about this. Sorry about that. All right. So, like I was saying, we're moving towards just visual examination. Great. So what we can do now is we can label directly onto our structure where our rotation is. And, well, actually, we don't. Uh, what am I trying to say? Ah, uh, sorry, I've lost my train of thought from my phone call. We can label. Ah, this is what it is. And what we want to do is we want to say, okay, right now, our rotation is what? Our rotation that's going on 1 to 2 to 3 is what? It's clockwise, right? And what does clockwise mean? It means R. Do we want R? Do we want R? Yeah, we do, right? So if the rotation is true, what do we say? We want that then our lowest group to be on the wedge, right? The rotation is true. So 4 has to be down, which means that this must be on the wedge. Okay? So it's this check here where we're comparing how drawing the molecule compares to what the name is telling us, comparing how we've drawn it to how we're naming it. And if this rotation is true, then we go with our old mantra, D is down. And so we put D down, which means that 1 has to be on the wedge. All right, let's take a look at, uh, let's take a look at, what do I want to do? You know what I'm going to do? Just to so that way we can talk about it. Put a methyl group on carbon 5. Okay, so in our name we can put 5 methyl. But I just want to be able to talk about what's going on a little bit so that we can really start describing things. All right, so for the last part, we're doing 4s, right? 4s. And what we can say on carbon 4 is, of course, we have 4 groups, 1, 2, 3, and 4. And we have a chlorine, we have a hydrogen, we have towards C3, and we have towards C5. Let me just erase some of these things so they're not as distracting. All right. And what we can say is that we know that chlorine will win. We know that hydrogen will lose. And who's going to win? Carbon to carbon, they're exactly the same. So for carbon 3, we can say it's bonded to carbon 2, a hydrogen and a hydrogen. For carbon 5, it's bonded to a methyl group, which I'm going to label as CM, mostly because I didn't give it a label, so that's what I'm going to call it, CM for methyl. It's bonded to C6, and it's bonded to that hydrogen, right? So who's going to win? Well, carbon 5 will win, so it's going to get the higher priority. Well, 1, 2, 3. So what's the rotation pattern that we have? Well, it's clockwise, right? Clockwise rotation. And what does clockwise mean? Clockwise means R. But do we want R? No, we want S, right? Did I label this right? Yeah, we want S. So we do not want the R rotation. We want to flip it. And how do we flip it? Well, we make sure that the lowest priority group, or 4, is on the wedge. And if 4 is on the wedge, that means this chlorine must be on the dash. So notice what we did. We determined that the rotation, the way that we've drawn it, is clockwise, and clockwise means R. It always, always, always will mean R. Clockwise will always mean R. Do we want R? No, we do not. So we have to make sure that we swap the rotation. Okay. Just because I know people would be wondering, yes, technically C5 is now a chiral carbon, but I didn't give you the chirality up here, so it is what it is. If you wanted to be so special, we'll say that it's 5R, and you can come up with what it should look like. But it should be on, if it's 5R, it should be on the wedge. So if you've done it right, congratulations. What do I want you to notice, however? Okay. Last part, and then I have to finish up right and quick. All right. So here's our molecule that we were working with, right? Can you see this? The screen? Okay. Whoa. Uh, Here's our molecule that we were working with. What I'm going to tell you that what's going to happen, you're going to be doing these problems with friends. You're going to be doing something. Okay, there we go. And what's going to happen is you're going to end up getting different answers. Okay. And let me show you what happens. Oh, whoops. So you're doing this problem with your friend, and what is the only difference between what you and your friend have done? Okay. Now remember that we draw it first and then we check it, right? And what do you notice? That when you drew it, you are the kind of person that you go up first. So you go up, then down, up, then down, up, then down. But your friend is someone who goes down, then up, down, then up, down, then up. And what do you notice? Actually, I think it should be like, I feel like this is, what am I doing wrong here? We could talk about this. And let me put it back to the way that it was. How did it? I don't know. I'm going to stop fucking with it. That's basically what it is. And you're working with your friend, and your friend's like, I can't figure this out. What's it going to be? And you're like, oh, it's wedged and dash. Okay. And that's what you tell them. Well, depending on how you draw your molecule, whether you go up first or you go down first, it changes what the answer is. Okay. So you have to be careful because if you look here, if they drew it downwards, they drew it opposite to how you did it. And look at what the name changes 2S, 4R versus what it should be is 2R, 4S. So what I'm trying to just get to you is that if you're doing these problems with a friend or you're trying to compare answers or you're looking at a book and the book has a different answer, it could be because, someone drew up when you drew down. Okay. And so what you have to do is you have to get really good at doing these molecules so that way, no matter which way you did it, you know that you are correct. And if you're comparing it with someone else, even though the drawings might be different, you still get the same answer. Okay. So, um, what am I trying to do here? The last thing I want to say about this is once again, you have to practice material. You cannot, this is not the kind of thing that gets easier. Okay. There are always more and more complicated problems out there, especially on these exams. Okay. They're going to give you some easy ones and they're going to give you some really hard ones. Okay. And you have to be good at it. If I just pull up real quick before we have to get going, because my next tutoring session. Um, when you're on your exam, you're going to be given molecules like this, all right? And they're going to be really big and scary, okay? But if you actually go in and you look at what the molecule is doing in one position, this isn't actually that bad, right? This is stuff that we've done. And look, oh, we're going to have some ghost carbons going on. Same thing over here, more ghost carbons, more ghost carbons. So you have to be good at looking at molecules in their different ways. Um, Same thing here. How many chiral carbons? Well, look at how complicated this molecule is. So if you're not good at doing these things accurately as well as quickly, you're going to struggle on these exams. So what you can do is, I believe you guys had to memorize some drugs by now. Go look up your drugs. Go look at the drug structures and determine the chiral carbons. They always have a bunch. It's a really good thing to do. But yeah, steroids are another big one. Um, cool. All right, that is everything I have for today. Next time we come back, we're going to look at chair. Which, have you guys gone into chair yet in class? Yeah. Okay. We're going to look at chair and how chair works, and then we are after that we'll do um, probably do E and Z. All right, that should be good. Um, I'm going to stop the recording. I somehow moved this.